You got it?
Yes, sir.
So then you have to supply the record to the other sections also, because we do not need to record individually. So what we have discussed earlier, that in course of our discussion, we have seen that, okay, I need to go to the, I have to change the mode. Let's show setting, browse it individual window. Where I will be discussing something, okay, or setting something, you can pause your recording, okay? Can you hear my voice clearly? This book, Introductory Electrical Circuit by Dorf.
Yes, sir, in first year, sir.
In first year, yes. So probably we have discussed about up to this point in the last class, isn't it?
Yes, sir.
Okay, at that time, what we have discussed, that if we have a first order system, then the first order system will have a single characteristic root, that sometimes called time constant of the system. For your RL configuration, it is L by RTH. For RC configuration, it is RTH. And we have said that if we have our passive system, there is no any possibility that the time constant can go negative. L and C cannot go negative. There exists a possibility that the Thevenin equivalent resistance or Norton equivalent resistance can go negative if your system contains some dependent sources. In that sense, what will happen, the term that contains exponential R by LTH or exponential T by RC, those terms will grow with time and your system become unstable. That situation can arise if your system will contain some dependent sources with some variable gain parameters. Consider this electrical circuit. Can you, because I have copied it from OSP. For this reason, your drawings are not that much clear, but still it is understandable. Can you understand this figure? That
Yes, sir.
we have an electrical circuit that contains a dependent source. What type of dependent source is it?
It's a current control.
Current control current source, exactly. And your switch was open for a long time. Then at time t equal to 0, your switch is closed. So you have your two states in your system, one before closing the switch and another after closing your switch. Then your dynamic state will begin when any change will occur in a circuit. But our change is occurring at t equal to 0. Then we have to derive the input-output relationship after closing the switch. But before, when switch was open, then your circuit was at a steady state. We need to know some of the quantities from that state that will be used as initial value for the next state. Okay.
Yes,
So
sir.
when our switch was open and your circuit was at a steady state, we have a capacitor connected there between these two terminals. Then your capacitor will be getting fully charged with a voltage. So no current will be going through this branch, isn't it?
Yes, sir.
Yes, sir.
For time t is less than 0.
Yes, sir.
So that voltage we are designating at V0, okay? So this is what your circuit for time t is less than 0. We can easily solve this circuit by using what? What law will be applicable there? Because this is a current source. You cannot calculate your voltage across the source directly, isn't it? But if you know the current I, then we can use Kirchhoff's voltage law there to find your voltage VO, isn't it?
Yes, sir.
Yes, sir.
So you can see that your current I is flowing in this direction. So if we apply Kirchhoff's voltage law at this node, what will happen? A current entering the node will be equal to current
Leaving the node.
leaving the node. So this is what this thing, and this will result you that your I is also 0. The if your I is 0, so these two terminals is behaving like an open circuit. So your VO would be equal to 12 volt. So that means your capacitor is charged with a voltage is equal to how many volts?
12 volts.
12 volts. Then that 12 volt will be appearing as initial value of the capacitor voltage after closing the switch, isn't it?
Yes, sir.
Then your next step is what? Your next step will be you just convert this circuit after closing the switch. You convert this circuit into a Thevenin equivalent. Then you proceed with solving the thing by using general equations that we have derived in our earlier classes, okay? Where we have seen that your output can be for a first order system can be written as y infinity plus y0 minus y infinity into e to the power minus t divided by time constant, isn't it?
Yes, sir.
Okay, that equation can be used. The next step will be what then? Our next step will be after closing the switch, you have to disconnect your capacitor. Then you replace the rest of the network by its Thevenin equivalent. Then you again insert your capacitor, then proceed with your solution, okay? So
Yes, sir.
this is what you okay, sorry. This is what your network after closing the switch. And after closing the switch, we disconnected the capacitor and your network is looking like this. Then I will not be going to deep detail into the system because this is actually the first year problem. Only the explanation will be a bit different. That is very important for us at this stage. Now you can easily apply your Kirchhoff's voltage law, current law, whatever law you need. Then you will calculate that your VOC is equal to this. And you see that your gain parameter beta is variable. So your VOC will also depend on beta. And by using your short circuit technique, we calculated IN. Then that if you divide our VOC by IN, that IN is not on current and it is equal to the short circuit current, okay? Then you will get your RTS known. Okay, from this point, the interesting thing will be coming out. You see that this RTH, is it not the function of beta?
Yes, sir.
Yes, sir.
Okay, for example, if your beta equal to 0, that current source is not there, and you see that your circuit is totally passive, and your RTH is always positive, isn't it?
Yes, sir.
Yes, sir.
Okay. Now, what is the boundary, for example, value of beta that will that boundary is between your plus and minus value of RTH?
Yes, sir. 3 by 2.
So
3 by 2. Okay, that means if your beta is increased by 3 by 2, then what will happen?
Negative resistor.
RTH will be negative. If your RTH is negative, then exponential term, this term will have positive exponent, isn't it?
Yes, sir.
Yes, sir.
If it is positive exponent, then what will happen?
Grow
Unstable.
over the time.
Then over the time, the response will grow indefinitely, isn't it?
Yes, sir.
Yes, sir.
So from this point, you have to keep in your mind that in general, a passive first order system is stable because there is no any possibility that for a passive circuit will give you RTH or RN equivalently negative. Then instability of a first order system will occur only when your RTH becomes negative. And that negative RTH results from the gain parameters of the dependent sources present in your network. So you can explore many of such systems on top of this. You will find many examples in the drop book. Drop books is very a good book. You see that where many examples are there related to practical applications.
Yes, sir.
So this concludes our first order. But before concluding it, let me again revisit the general form of first order equation when it will give you unstable result. Okay. So you can see that our first order general form of the equation was d dt plus ay was equal to say bx, something like this, wasn't it?
Yes, sir.
Okay, and you see that will give this solution will give you a homogeneous part that is equal to some constant E into AT, isn't it? And if your A is positive, that will always be decaying. But for our case, when system is unstable, then what will happen? Your d by dt minus ay would be equal to bx, something like this. In this case, the homogeneous part A would be equal to at, something like this. And this is unstable. Okay.
Yes, sir.
Actually, I have a health issue. For this reason, I cannot move my hand because in the a couple of days ago, I got, for example, probably at the night time, some insect were crawling over my body and some portion of my chest burnt. So this is our first order system. Okay, another in this context, I want to mention one thing, that although the things are there in your Haykin's book or Sadiku's book or whatever text I mentioned earlier, those things are there, okay? It starts from article 2.10 of your Haykin's book. Those things are very mathematical general. I always prefer to refer those things to some practical examples, okay? So the general thing is completely mathematics and you try to revisit them, okay? But
Yes, sir.
I will always refer those equations to some practical scenarios so that it will be understandable to you that how you can apply that thing to your field. Now we will be starting with a second order system, although some discussions about the system we have already made. Okay, consider that are those systems are active or passive?
Passive.
So passive.
All systems are passive. The reason is there is no any independent sources or any
Yes, sir.
dependent sources or any devices in them. Devices means some active devices, okay? Particularly the electronic devices like transistor, operational amplifier, or any of such devices. Your first figure is a series combination of an electrical circuit with three elements, R, L, and C. Second one is parallel. And third and fourth one is actually, you see, in one of my classes, I said that the order of the differential equation depends on the number of energy storage element present in your system, isn't it?
Yes, sir.
Yes, sir.
So in our earlier cases, we have seen that we have only one energy storage element present, either a capacitor or an inductor. And our circuit was a simple series circuit equivalently. But in the case of second order or higher order system, more than one energy storage element will be involved. Now we have our two energy storage element known up to this point. One is your capacitor, another is inductor. Now you see that those capacitors and inductors can be connected in series like figure A, or they can be connected in parallel like figure B. But in figure C and D, you see that in figure C and D, we have one type of uh, energy storage elements, isn't it? In figure C, it is inductor, and in figure C, capacitor, isn't it?
Yes, sir.
But the order of your system will be different. The reason is that this inductor L1 and L2, they are not connected in the same electrical locations. Electrical locations means they do not have anything in common in terms of current or voltage. Are those things are common to L1 and L2?
No, sir.
No, sir.
Because they are carrying different current and voltage across them are also different. So although they are of same type, but they are not located in same electrical locations. As a result, unless we derive the input-output relationship, we cannot identify the order. The same is true for your figure D, but we can readily say that figure A and figure B will be of second order type, okay? So the derivation will be left to you to be derived. Number one, because we will be using Kirchhoff's voltage law, current law, loop or node analysis to derive the equations. No new concept will be needed to do that. It is there in your electrical circuit. Okay, first of all, what you need to do, you have to identify what is your input. You have to identify where is your input. Next, you have to identify from where you are extracting what type of output. So in circuit A, we are assuming that because there exist many possibilities of your output locations. It can be current, it can be voltage across your capacitor, it can be voltage across your inductor, it can be voltage across your resistor. Any one of these quantities can be taken as your response or output. But this equation is derived by considering that voltage across the capacitor is our output. In the same way, we are considering that current through the inductor is our output. Okay, your output can be current through capacitor or voltage across your inductor or current. But if we know any output, the other quantities can be easily determined. So this is what the input-output relationship for your series RLC circuit in figure A. We have grouped our output quantities in one side and input quantities in other side. And the second case, your output is I. So we have written our equation in terms of I and put it into the left-hand side. And this is your input side. Okay. Now we can easily identify from equation 1 and equation 2 that they are of what order?
Second order.
They are the second order differential equations. So in a second order differential equation, how many characteristics root will be there?
2, sir.
No, sir.
Okay, we will discuss it again because this is, okay, look, from this point ahead, are those problems are electrical or mathematical?
Sir,
Mathematical, sir.
Mathematical. So that mathematical technique, that's why you have already been given some background with your necessary mathematics. We do not need so many mathematical things, but we need some mathematics. Unless you know it, you cannot proceed further as an engineer. So this is your equations of second order, and they are ordinary differential equation. We can easily solve it by using our mathematical procedure that you learned. Now we consider our figure C and D. So you see that in figure C and D, either you can use your nodal analysis or you can use your loop analysis to derive the resulting equations. So in figure C, which technique will be more suitable?
Loop analysis.
Loop.
Loop analysis. So you can easily find the loop analysis. Look, this is not a resistive circuit or an hysteresis circuit. But as transient or rate of change will be available, voltage or current related to capacitor or inductor should be written in differential equation form. So your first equation is the loop equations for loop 1, isn't it?
Yes, sir.
And your second equation is the loop equation for loop 2. Okay, these two are the differential equations, are not they?
Yes, sir.
Okay, can you merge them to form 1? Because in your differential equation, rather than a single equation, you can also solve simultaneous differential equations. And they are coupled because the variable of one, because our objective is what? Our objective is to find, say, current I1 and I2. Then you have to solve these two equations simultaneously. Okay. Or what you can do, you can use some operator algebra just to solve for, say, if we assume that I2 is our desired output, then what you need to do? You have to solve this equation by using what? By for I2. Similarly, in the next second equation, you can apply your Kirchhoff's voltage law at the two nodes, then you will obtain this equation. Here, your V1 or V2, any one of this quantity can be your output. That in this case, you can solve those equations simultaneously to find the input-output relationship. Now you see that in your differential calculus or your differential equation, sometimes the derivative, say d by dt, can be represented by an operator, say S. Have you learned about it?
Yes, sir.
That means if this is an operator, then these two equations can be written in the form of operator. That means the upper equations will be minus Vs plus R into I1 plus Ls into I1 minus I2 is equal to 0. Can you write this in this way?
Yes, sir.
But do not confuse it with your Laplace variable, okay? This is your operator. Look, when we are using operator, then you have to maintain the precedence of operation. Okay, for example, if we are writing, say, d by dt, say, A, in operator, it will be equal to SA, but it will never be A into S, okay? This operation is not allowed. Your operator should precede the operand. You got
Yes,
this
sir.
point? And
Sir.
accordingly, you can solve your equations to find I1 and I2. Then you again go back to your differential equation by replacing S by this operator, okay? So in this way, you can solve these two simultaneous differential equation for either for I1 or I2 or for V1 and V2. Then it will give you a single differential equation of second order. Then you can easily see, you will easily see that your figure D and E, no, C and D are also second order type. Okay, let us move to the next slide. We'll be illustrating with an example. Okay, so after having this general concept for passive circuit just discussed, we can proceed with solving our equations by using our technique that we have learned. Okay, few things are there you have to consider in solving your differential equation. In some books, some confusing terms are also there. But regarding the solution in terms of signals and system strategy, the discussion that I made earlier will be, you have to keep in your mind so that it will not give you any confusion. Let me share the whiteboard to discuss this issue, okay? Probably in your in your Haykin's book, some confusing terms are there. We have to identify that from where the confusion must arise. You see that we have categorized our output Y as two parts, isn't it? One, we called it zero input response, and another part was called Y what?
ZSR.
Zero state response, isn't it? Your zero input response will not contain any input, and your zero state response will contain the input. Okay. Your ZSR will contain two terms. One is called transient. Another is
Steady state.
the transient part will contain the characteristic mode of your system. Characteristic mode, okay, that will result from the parameter of your system. Okay, in first order system, that characteristic mode is synonymously called time constant. Okay, But the steady state behavior of your network actually replicate the nature of your input. Okay, if we have a DC, then your output in long run will be DC. If we have an alternating current, then your output in long run will also be alternating. We will be discussing about it, how the steady state quantity depends on the nature of your input. Okay, but your YS, this quantity, for example, YZIR, it results from where? It results from your initial condition, isn't it?
Yes, sir.
And the nature of your solution is this type, e to the power lambda t or something like this, okay, like your transient part. And here we will have this quantity that is also the characteristic mode of your system. No input will be there. Now the question is how they are related to our differential equation. In differential equation, again, this solution can be categorized into two parts. One part is called homogeneous solution, another part is called particular integral, isn't it?
Yes, sir.
That particular integral actually contains only the input, but it will not contain the transient. Okay, for this reason, this part is your steady state. You got my point?
Yes, sir.
Yes, sir.
This part will never contain any, it will only input will be there, and that part will not contain any what we call transient. So characteristic mode will not be present in particular solution. But the transient mode will contain both. Then your YS will contain what? It will contain both your transient plus ZIR. Both part will be contained in YH. For in many of your texts, this quantity YH is called natural solution,
Yes, sir.
or it is called homogeneous solution, or we call it complementary function, isn't it?
Yes, sir.
Complementary function or complementary solution. So, but no matter in which name we call it, natural, homogeneous or complementary, but this is not equal to ZIR. You have to be careful about that. The reason is that region is in the technique of determining the integrating constant. If we determine the integrating constant after obtaining, for example, say your YS we obtained. After obtaining your YS, we apply initial condition, apply ISIS. After application, you will find the initial integrating constant there. Once those integrating constant is available, then you can use, for example, YT as an independent solution. In that case, it will be equal to your ZIR. You got the point?
Yes, sir.
But when after obtaining, for example, after obtaining your YS that will contain integrating constant, we will not determine the integrating constant at a stage. Then we obtain YP, the particular integral. Then we obtain the total solution YS plus YP. After having this thing done, apply initial condition.
Yes, sir.
Initial conditions. Then you will get a solution there where your transient, your ZSR and ZIR all will be embedded. You got my point?
Yes, sir.
Yes, sir.
Let me reiterate it, okay? So you have used total response. That total response in terms of a solution of differential equation will contain principally two terms. One is YH, the homogeneous solution, complementary function, or natural solution. Another part is particular integral. Your particular integral is the steady state solution, and your homogeneous part contains both your transient and ZIR. Your ZIR can be determined only when you apply your initial conditions after solving for your YH. Then the solution will give you ZIR. But when we add our YH with YP, then apply initial conditions to find the integrating constant, then your total solution will contain all the individual component, but they will be embedded together. That is the technique, okay?
Yes, sir.
Okay, fine. Now, the thing I have already discussed. Okay, your general approaches, you see, your JDIR solution will have this type of nature. You have seen this thing in your, for the case of first order. All the, for example, thing will have this form, because JDIR in a stable system cannot grow indefinitely, okay? It will eventually die out. The reason is that if we do not apply any source to a system, then can you expect that your output for a stable system, that your output will continue?
No, sir.
No,
It will
sir.
decay.
It will not continue, it will be dying out. As a result, we will have a characteristic root lambda j there. That lambda j in your Huygens book, probably it is represented by tau or other notations. You compare the thing with it. So that quantity lambda I actually is called characteristic mode. Characteristic mode, okay? It will contain, for example, what the thing, all the element that involved in your network by some or other will be migrated to this mode, okay? Now we have our ZIR, ZSR. ZSR is due to the input xt, but that ZSR can be calculated in different ways, either by solving differential equation or by using convolution, okay? The convolution technique that we studied earlier in the chapter for discrete time and continuous time cases is actually for ZSR. So we can use your convolution, or if you do not use it, then we can solve directly from differential equation. Convolution operation is possible only when the impulse response can be determined. In our preliminary cases, we assume that our impulse response is available, or in some simpler cases, we have given the input-output relationship from where we can obtain the impulse response. But for a continuous time system, you need a different technique of finding the impulse response. Although, meanwhile, you have learned about transfer function. So you can also apply your Laplace transform to find the impulse response, because impulse response is the Laplace inverse of what?
Impulse response is the Laplace inverse, sir.
The transfer function.
Of transfer function, okay.
Yes, sir.
Yes, because you know that transfer function is the ratio of input and output. When your input is a delta, then Laplace transform of your input would be equal to 1. As a result, your output would be equal to HS. And then this HS is called transfer function. And when we take inverse of this transfer function, you will get your what is called impulse response, okay, in time domain. So when nothing will be mentioned, you can apply any one of your technique which is comfortable to you, okay?
Yes, sir.
Now let us go quantitatively. Okay, in your first circuit, the RLC1, the following, although those things are not new, you have already studied in your second course of electrical circuit, okay? But we'll simply revisit it. You see that for that RLC circuit, if we have our values of R, L, and C given something like this, 3 ohm resistance, L equal to 1 Henry, C equal to 0.5 Farad, and we applied a VS, that means source, is equal to 10 e to the power minus 3 UT. It is what type of source? It is an exponential source, okay? Forget about giving the reasoning of the reality of this thing, but for illustration, we are using this, okay?
Yes, sir.
Now, if we put this thing to our general equation that we derived in first slide of second order system, we can readily obtain this equation. What form of equation is this? Okay, I have given the operator D because in many of your cases in your mathematics, you replace your differential operator by D, isn't it?
Yes, sir.
Yes, sir.
So if we operate this D, you see that D2 doesn't mean that it is D square. If we have a second derivative, then it is D2, okay? If we have a first derivative, it is D. So this exponent will give you the idea about the order of your differential equation. So our order is a second order differential equation. Now, in terms of your operator, we can easily write this equation there. Now, I will not be going to deep detail to it. You know this thing. You see that we have our two solutions will be there. Okay, one is your homogeneous solution, another is particular integral, isn't
Yes,
it?
sir.
Or in terms of system engineering, we can find from homogeneous solution, we can find our ZIR. Now, already we have mentioned that our homogeneous solution or ZSR will have a general characteristic form of e to the power lambda t. Okay.
Yes, sir.
This is what your general solution, then if we apply this general solution to the homogeneous part of your equation, then what will happen? Your d2 will be equal to what? It will be simply equal to lambda square into y plus 3 into lambda y plus 2 is equal to 0, isn't it?
Yes, sir.
Yes, sir.
Or not y, actually it will be equal to e to the power. Okay, let me erase it. It is not y.
To the lambda t.
It will be equal to what? Because your d2y would be equal to lambda square e to the power lambda t, isn't it?
Yes, sir.
And your dy would be equal to lambda e to the power lambda t. And your y is equal to e to the power lambda t. Then as your e to the power lambda t cannot be equal to 0, then this would be equal to 0, isn't it?
Yes, sir.
The name of this equation is called characteristic equations of the differential equation, because the characteristic nature or mode of your system will be translated to this equation. Now the root you have to find what are those characteristic modes of your system. So those characteristic modes can be calculated, can be identified by solving for lambda. How many values of lambda we will have there?
Two values.
2. And those lambdas are, because you see that this is a quadratic equation of lambda, isn't it? Many possibilities could exist. But as our values are given, with those values of circuit parameter, we obtain that our lambda has two roots, and both roots are real and what?
Imaginary.
Are imaginary. Are this imaginary? They are real
Yes,
and
sir. Yes, sir.
negative.
Distinct.
They are distinct or unequal. They are real and unequal root, but they are negative. If any one of these root become positive, then your system will be unstable. The reason is that any one of the term e to the power lambda t becomes will grow with time. So for a stable system of this type, for this particular value of RL and C, we are obtaining two roots. One is -1, another is -2. As a result, your natural this solution, natural solution or homogeneous solution will take this form. Okay, a linear combination of these two terms will be there. Then these constants C1 and C2, you have to calculate. If we calculate our C1 and C2 at this stage, then we will be obtaining YT completely, YNT. Then what will be the name of that YNT in terms of our signals and system?
ZIR.
ZIR, exactly, very good. So it will be equal to ZIR. Now we have to calculate the force response or the response due to the input. In this case, we will follow a technique is called method of undetermined coefficient. Okay, in this connection, I am referring a table to you from your Haykin's book. And that table is table 2.3. Okay.
Yes,
Or
sir.
if you have a B.P. Latti's book, then I have already mentioned the page number and the article number. Okay. Or even in your mathematics book, you will find this thing, method of undetermined coefficient. Okay. If we want to give just one sentence description of this method, it is simple. Just you can say that your output for a particular processing function or input will follow the input. As a result, a relationship can be developed between the input and output for particular solution, and that solution will contain some constants or coefficients that we will not know, that we need to determine. That's why it is undetermined coefficient. How can we say this? It is simply an approximation technique of solving differential equation. And in most of our cases for analytically solving differential equation, this technique will give you fairly accurate result. So we need not to go to some complicated method at this stage. Okay, so according to this method, what we have discussed, that your input will follow what? Now your output will follow the
Input.
input. So what is the nature of the input that we assumed for this particular problem?
Exponential.
That your input is of this type, isn't
Yes,
it?
sir.
What is the type of the
Yes,
input?
sir.
Is it not exponential? Okay, with a root equal to, with a factor e to the power minus 3 is there, but be careful about choosing this type of forcing function. This special issue is discussed. This special issue is discussed in article 2.10.2. Okay, you go through it, Haykin's book, that what a special issue is involved there. What is that special issue? If, for example, if your input is of this type, exponential, if this exponent is very similar to a characteristic root of your system, if this factor coincides with any one of the roots of your system, then you have to modify your solution. Okay, you know which ways you need to modify it, that is described in article 2.10.2. You try to go through it. It is not very difficult. We will also discuss about it a bit when we will discuss that, because you see the root of characteristic equation are the factor that will determine the ZIR or homogeneous solution of our differential equation. So if any one of this characteristic root will coincide with your input characteristic, then we need to modify your solution, number one. Second thing is that those roots can be a repeating root. Do you know what is repeating root? That means root with same value of lambda. The if your characteristic roots are same, then you have to write your general solution of differential equation in a different way. You try to have a look from your mathematics book about when your roots are equal. We will also revisit it here. So in this case, this thing will not occur, because we have our two characteristic root. One is -1, another is -2. So here it is e to the power -3. So they are distinct. Now, according to our method of undetermined coefficient, the force response will have the same form. That means it will also be exponential of this form, but it will contain a constant. That constant or coefficient, something like this. Our solution will be a e to the power -3 ut. This solution is what solution? It is for your particular solution. That is solution due to input. Now, here a, we do not know the value of a. That a we have to determine. And another important thing is that your differential equation has two solutions. each of the solution, okay, one is homogeneous, another is particular. If this is your particular solution and your particular solution is actually steady state solution, if we assume that this is what your solution, then that solution must satisfy the differential equation. Our original differential equation was what? D2 plus 3 into D plus 2 was equal to what? 2 into X, wasn't
Yes,
it?
sir. Yes, sir.
Yes, sir.
So that our solution, we are now solving for YP particular. And we are assuming that our Yp is equal to a e to the power minus 3t ut. We are solving our system for time t is greater than 0. Now, if this is your solution, that must satisfy this equation. So if we put this equation, put this value of Yp in this equation, then you take the derivative twice, it will be equal to minus 3 into minus 3 a e to the power minus 3t. This is what. And in the second case, it will be equal to minus 3 into 3 e to the power minus 3. This is what this case. Your third term will be equal to this, equal to your input. Then you see that this e to the power minus 3t cannot be equal to 0. Then you can readily solve for your undetermined coefficient a, and you will see that that particular solution of your problem is this. So your particular solution, we are following the classical technique of solving differential equation. So in this case, what will happen? After having your particular solution obtained for the particular input, we have obtained the natural solution or homogeneous part earlier. We have obtained this thing now. Then your total output YT would be equal to this. The next thing is what then? You have to find C1 and C2. You apply your boundary condition. Okay, your boundary condition is defined in this way. Say your VC0 minus is equal to VC0 plus equal to 5 volt, and this will be equal to Y0. And your current, for example, V0 minus and I0 minus would be equal to 0. Then if you want to apply, for example, the boundary initial values to your YT, how many initial values will be needed?
2.
2. Then these two initial value will come from where? One will come from your capacitor, another will come from
Inductor.
inductor. Okay, your capacitor voltage is given, then you have to calculate the inductor current. Your inductor current is equal to capacitor current. So that will be equal to C dVc by dt at t equal to 0. And you know how to determine it. Consult with chapter 8 of your Alexander Sadiku's book to find the initial values of an electrical circuit. So having these two initial value obtained, you can easily set these values, and your inductor was not carrying any current actually. So after closing the applying the input, your current will remain unchanged. So it will be equal to 0. So once these two initial values are okay, you have this one initial value there, you have your second initial value. You have to apply this initial value directly to there for setting t equal to 0. So your one equation you will obtain, then you take the derivative of this equation to obtain this current, then you put the derivative equal to 0 at time t equal to 0. Then how many equations we will have?
2 equations.
We will have two equations there.
Yes, sir.
Yes, sir.
So these two equations, this is one, this is the second one. You can easily solve these two equations to obtain your C1 and C2. So this is what your equation. Now you see that your response, this is your force response, or it is your particular solution, and that contains only the input. But this solution is your natural response. How many components are there?
2 component.
2 components. One is
transient, another is steady state.
Isn't it?
Yes, sir.
Yes, sir.
Unless you calculate your ZIR separately, the transient part cannot be extracted. Okay. You can how to find the ZIR. Okay, when we obtain the solution C1 e to the power minus 1t plus C2 e to the power minus 2t, we obtained y ht, say at this point if we apply the boundary condition, the initial condition, then we will obtain a solution there. In that case, the value of this C1 and C2 will not be equal to this value of C1 and C2. Okay, then when we apply our initial conditions to YST, then this solution will be equal to ZIR. And if we subtract this solution from this equation, you will get the transient part. But when you are asked to find the total solution, any one of the technique you can apply. No problem. But when you will be asked to find your ZIR, then you have to calculate the ZIR separately. Okay.
Okay, sir.
Yes, sir.
So I have already discussed about ZIR. Okay, you take a look. Your ZIR is equal to this. Now I will be discussing about how to find the. Okay, now in other cases, the general technique will be exactly same. The technique is what? When your system will be given, you derive the input-output relationship in the form of differential equation. Then you apply your solution technique there just to find the output. That's it. But if you want to follow the process that we have to find your ZIR and ZSR separately, so you have seen that your ZSR involve convolution. You have to convolve your input with impulse response. Then you have to know how can we find the impulse response. One of the technique is Laplace transform that I have already discussed, and you know this probably from your control system theory. Now I will be introduce something without giving any rigor mathematical explanation. Just how can we determine it from time domain solution. Okay, because this technique needs further investigation of the differential equation. Okay, one important thing is that, just let me, for the sake of discussion, I am doing this. Okay, you have to go further if you want to go into it. Okay, for example, say if we have a second order differential equation dy by dt2 plus a dy by dt plus by is equal to say xt, something like this. Now we are considering that if your xt is equal to del t, then your y would be equal to ht, isn't it?
Yes, sir.
Now tell me, if we have a second derivative there, say this is your y, I am calling it now h, dt 2 plus a dh dt plus bh is equal to now delta t. Now you can easily identify that what will be the nature of our solution. If we have a solution of this type, can you tell me that what will be the, just for intuitively, that what will be the nature of H? Your nature of H can easily be determined by examining the input-output relationship. You see that the highest derivative is the second derivative, isn't it?
Yes, sir.
So the second derivative of the quantity must be a delta, otherwise they cannot be equated. Can you equate them? If your left hand side will not results in a delta after your total solution? A very simple thing. If your right hand side contains a delta, then when these two sides can be equated, if your left hand side will result in a delta, isn't it?
Yes, sir.
So that you have to consider that particular logic is applied in obtaining the general solution for considering a general solution for determining the impulse response. Okay, I have extracted this topic from BP Lathi's book, but you can find in any of your text. Probably this is not there in your Haykin's book. Okay, in your Haykin's book, your differential equation is written in a different way, general form, but it is the normalized form. Normalized form means what? The highest derivative is set to coefficient equal to 1. So if we write our equation in this way, you can proceed with writing this equation in your own style. That will not be creating any problem. But the thing is that you have to know the underlying mathematical technique, how to proceed with. So this is your input side. This is your output side. Both sides can contain derivative. So in order to proceed with for the derivative of notation, the operator algebra is used. Then your derivatives are replaced by the operators. Then you will see that we will have a polynomial of operator in the output side. This is represented by QD. And we will have another polynomial of operators at the input side. This is represented by PD. Then if we have our impulse response to be determined in general, then this is what the technique. Okay, we have our both your PD and QD will be known to us. Then our impulse response can be determined in this way. That the generalized form of the impulse response of this nth order system will have equal to this form, St equal to Bn delta T. That Bn delta T will only exist when Bn is non-zero. That means if your order of your input polynomial and order of your output polynomial will be same, that will give you the value that will give you a term equal to delta in the impulse response. Okay, can you give some example of this type to me from the knowledge of your control system? When a delta can be there in the impulse response?
Sir, when there is a sudden force applied.
Okay, because in your control system, you have seen that your control system, you obtained your transfer function, isn't it?
Yes, sir.
Your transfer function, say for a simple RC type circuit, your transfer function can be say S plus 1. If we take output across a capacitor, then your ST would be equal to e to the power minus t, something like this, isn't it?
Yes, sir.
Yes, sir.
In the same circuit, let us consider that you are taking output from the resistance. Then your H would be equal to what? In this case, your H would be equal to S divided by S plus 1. Then what is your ST?
Sine.
Sorry? একটা প্রবলেমও সলভ করতে পারো নাই ক্লাস টেস্টে, দেখা গেল যে সবাই সলিউশন জমা দিয়ে দিছো ইয়াতে কি বলে ওটাকে অ্যাসাইনমেন্টে। এখন সবাইকে তো 15-এর মধ্যে 20 দিতে হয়। আল্লাহ ভরসা। কত এটা what is your response?
Sir, it will be a cos.
It is cos. Is it cos? Can you just write it in this form? Because your cos term must contain a quadratic term in S.
Sir, t to the power e, sir, t e to the power minus t.
E to the power minus E.
Sir, e to the power minus t.
This is e to the power minus t for 1 by s plus 1. Is it the same answer?
No, sir.
Can you factorize it? Is it not, for example, it is equal to 1 minus 1 to s plus 1?
Yes, sir.
Then what is st?
Sir, there will be a delta. Yes, sir.
Now can you understand why delta can be there?
Yes, sir.
So if your order of your input output side will be same, then that can result in a delta in your impulse response. Try to learn more about it by using your control theory learning, okay? Only theoretical basis is not important in learning engineering. Be careful about that. If you cannot relate it with physical system, there is no any significance of learning engineering. Now you see, that's why the general form is represented in this way, okay? Now the question is, what are the thing, okay? If you Bn will be given, if you know the input derivative, Bn will be determined. Not all system will contain Bn. So your delta t, this term may or may not be present in your solution, but the second term must be present. Your PD will be there from your output input polynomial. Ynt is the natural solution, that means homogeneous solution. Then this Ynt determination is a bit different from the determination of Yn that we have illustrated earlier. In this case, we will have to use some auxiliary initial condition. These are the auxiliary initial conditions are given there, okay? I have already uploaded this thing to your Google Drive. Before attending to the next class, okay, try to have a look. I will be finishing today's lecture at this time. You can stop your recording, please.